Welcome. In this session, let's explore how we can use an artificial neuron on Fisher's iris data. So let's recall Fisher's iris data uses petal data. He also collected sepal data. We'll just look at the petal data. And our observations are the petal length and width. And we'll label these as Y if it's the species Iris setosa, and we'll label it as 0 for the other two species. So this is what our original data looks like, is that in these cyan, including this one over here, these are all Iris setosa petal length and petal width. And then these are the accumulated petal widths and petal lengths for the other species. Our binary classification task is that we want to be able to produce classes that are exactly equal to the labels. So our assumption is that for every one of these augmented data, we'll say that it's in set 1 if the label is 1 and 0 otherwise. So the ideal match is that when the label is 0, that the linear response is less than 0, and if it's 1, then that corresponds exactly to when the linear response is greater than or equal to 0. So for a sigmoid or logistical activation, what we'll do is, when I did this computation, I used a learning rate of 0.03 and the steepest descent that we've been going through in the last couple of classes. And this gives us an optimal linear classification. So when I take the iris data and I run it through a very simple artificial neuron, which is using logistic activation, this is the separating hyperplane I get. We observe that it just barely catches this sample down here, but it does in fact capture all of the data correctly. So what have we learned in this class? Well, you should now be able to compute augmented data for the purposes of doing neural network computations. You should be able to formulate the iteration of steepest descent, and you should be able to compute this iteration using multiple data as we just observed.